The quantum world represents one of the most enigmatic and fascinating fields of modern physics. In this realm, operating at subatomic scales, the natural laws we perceive in our daily lives seem to collapse, giving rise to a set of phenomena that challenge our intuition and understanding of the universe. While classical physics, emerging with the works of Newton and other great scientists, describes the movement and forces acting on macroscopic objects, quantum mechanics introduces us to a domain where the rules are radically different. This paradigm shift in science has not only allowed a better understanding of the behavior of matter and energy, but also led to technologies that have transformed our daily lives. However, the most captivating aspect of the quantum world is not just its practical applications, but the profound philosophical questions it raises about the nature of reality, time, space, and the observer's role in the universe. To comprehend the quantum world, it is essential to review some of its fundamental concepts. One of them is wave-particle duality. This phenomenon, first observed in experiments with light and later extended to particles like electrons, establishes that matter can behave both as a particle, with a defined position and trajectory, and as a wave, spreading through space and generating interference patterns. A key experiment that illustrates this duality is the double-slit experiment. When a beam of electrons passes through two slits and the system is not observed, the electrons form an interference pattern on a screen behind, similar to wave behavior. However, when it's measured through which slit each electron passes, the interference pattern disappears, and the electrons act as individual particles. This phenomenon, defying classical logic, suggests that the behavior of particles depends on how we interact with them, questioning the idea that the properties of objects are intrinsic and independent of observation. Another crucial concept of quantum mechanics is superposition. This principle states that particles can exist in multiple states simultaneously until a measurement is made. Mathematically, this idea is described through the wave function, a tool that assigns probabilities to the possible states of a system. A famous example of superposition is Schrödinger's cat thought experiment. In this scenario, a cat locked in a box can be simultaneously alive and dead until the box is opened and its state is observed. Although it seems absurd from a classical perspective, this experiment illustrates how quantum systems can coexist in seemingly contradictory states, at least in probabilistic terms, until they are measured. Quantum entanglement is another fascinating phenomenon that challenges classical ideas of causality and space-time. When two particles interact and become entangled, their states become connected, so that any change in one instantly affects the other, regardless of the distance between them. This phenomenon, which Einstein dubbed spooky action at a distance, has been experimentally confirmed and raises fundamental questions about the nature of reality. Entanglement is not only a topic of theoretical debate, but also has revolutionary practical applications, such as quantum cryptography. This technology uses entanglement to ensure absolute security of communications, as any attempt to intercept the information would alter the system in a detectable manner. Heisenberg's uncertainty principle is another pillar of quantum mechanics. This principle states that it is impossible to measure both the position and momentum of a particle with absolute precision at the same time. This limit is not due to deficiencies in measuring instruments, but to an intrinsic property of subatomic particles. The more precisely one property is known, the greater the uncertainty in the other. This principle underlines the probabilistic nature of quantum mechanics and challenges the idea of a deterministic universe, where, with enough information, we could predict the future of any system. The development of quantum mechanics was marked by a series of experiments and theories that revolutionized our understanding of the world. The photoelectric effect, explained by Einstein, demonstrated that light is not only a wave, but also has a corpuscular nature, comprised of particles called photons. This discovery, which earned Einstein the Nobel Prize, was one of the first pieces of evidence that energy is quantized. Schrödinger's equation, introduced by Erwin Schrödinger, provided a mathematical description of how quantum systems evolve over time. This equation is fundamental for understanding the dynamics of subatomic particles and remains a central tool in modern physics. Despite its apparent abstraction, the quantum world has practical applications that have transformed our society. Quantum mechanics is the foundation of technologies like transistors, which are essential for modern electronic devices, and lasers, which have applications in medicine, communications, and data storage. More recently, quantum computing has emerged as a promising technology that could solve problems beyond the reach of classical computers. Quantum computers use qubits, which can be in superpositions of states, allowing them to process information exponentially faster for certain tasks. This could revolutionize areas like cryptography, artificial intelligence, and the simulation of complex molecular systems. In addition to its technological applications, quantum mechanics raises profound philosophical questions. The Copenhagen interpretation, one of the most influential, suggests that quantum reality is not defined until observed. This has led to debates about the observer's role in creating reality. On the other hand, the theory of many worlds posits that all possible states of a quantum system exist simultaneously in parallel universes. These ideas not only challenge our understanding of the universe, but also touch on fundamental questions about the nature of consciousness, time, and space. The quantum world also has cosmological implications.